Hello everyone. So I'm going to record a review of the lecture worksheet number 4. Right now I'm using my headphones, so if my voice is a little bit too high or too low, then we can work on it as we go. And I can speak louder or less loud. Alright, so I did a little review on the lecture worksheet number 4. And I'm going to do example number 1, which was the equivalent resistance examples. And then before going to example number 2, for Kirchhoff rules, I will give you a brief overview of Kirchhoff's rules in a different video. So this is just to get started with this new format. I'm just writing my notes on Notepad. So you can all get acquainted to this. Alright, so last time we met, we had a combination of resistors. So I'm going to go over resistors in series first. So here, for the resistor in series, in this beautiful yellow diagram, we have a battery, which will give us a potential difference. Okay, so here we have a potential difference from the right side to the left side of the circuit. And we have R1 and R2 denoting the first and the second resistor. Now, because this is a resistor in series, the current only has one particular direction that it can go. So here, the current is the same in the two resistors, because any change that goes or flows through the first resistor must also go through the second resistor. Okay, so any flow that goes to this first resistor will also go through the second resistor. So, using the same analogy, you can think of a flow of water that if you have any type of resistance, think again of like some stones, then the flow of water will go through this first and the second resistors. On the other hand, if you look at the potential difference here, the potential difference across the resistors, so between resistors 1 and 2, is the same as the potential difference across the combination. Okay, so in other words, here if I want to find the potential difference T, it will be for total. The potential difference total is the potential difference through the first resistor plus the potential difference through the second resistor. Alright, now if I want to add these resistors, then to get the equivalent resistance of these two resistors here, I'm going to add R1 and R2. Then I can combine them to make one equivalent resistance, and I'll call it R equivalent here. And to add the equivalent resistors in series, we can just simply add these resistors, and you're going to have R1 plus R2 plus ... meaning that if you have more resistors, you just keep adding them more resistors. Alright, then we talked about resistors in parallel, so circuits that have resistors in parallel. So here we have a, beautiful circuit in parallel. So here we have a battery with a potential difference between the right side and the left side of this battery. And then we have resistor 1 and then resistor 2. Okay. Now this location A and B, at this location, these are what we call nodes or junctions. Okay, when we talked about Kirchhoff rules, I'm going to call them junctions. And at this location, the current will have an option. So at this location, the current, think of the current going up right here, and it can go to the right or up. Okay, so you can call this I. I can call this right side I1 because it came from, or is going to resistor 1. I'm going to call this I2 because it goes through resistor number 2. And so here we see that the current will be split, but the left side, let me change the colors for red. The left side of both of these resistors and the right side of both of these resistors are connected to the same side of the battery. So these two reds are connected to this, green again, this positive end. So red, red, positive. And then the blue ends are connected to the negative side. Okay. What this means is that potential difference between, let's say, the blue and the red is identical to this negative and positive side. So that is why the potential difference across the resistors are the same, because each is connected directly across the battery terminal. Okay, that's another way to say that each is connected to the red, the positive, the blue, and the blue to the negative. Now, what this creates will be a set of equations. So, if I want to say that the potential difference is the same, then I can say the change of potential between the battery, let's call it delta V, is equal to the change of potential in V1, which I'm going to call the potential through the first resistor, and then the change of potential 2, which goes to a second resistor. Alright, and adding to this current here, so the white, so many colors, adding to this idea that the I, which is the current going through this battery, is split into I1 and I2, I'm going to write that equation in terms of the conservation law. So here I have current is conserved. Okay. What that means is that the current cannot be created or destroyed, is basically split in two and then recombined. And so the current I that enters point A must equal the total current I1 plus I2. So in equation format, I can say that I is equal to I1 and I2. So here's where we get the equivalent resistance for parallel. Now I'm going to apply, let me use green again. So I'm going to apply Ohm's law. Okay. So for Ohm's law, I remind you that Ohm's law is that the change of potential is equal to IR. And I'm going to plug the I1 and I2 from these equations and rearrange them and then just put them back there. Okay, something like this. So here I have I1 will be the change of potential because the voltage drop is the same for the circuit, divided by R1. So the current through the first resistor determined by the first resistor, and the current through the second resistor determined by the second resistor. Okay. So plugging I1 and I2 into the top side and noting that just the current through the battery is the potential difference divided by R equivalent, as if you combine all the resistance. I have the following. I will have, again, I'll remind you that I'm writing this. I'm writing I is equal to I1 plus I2. So I have delta V over R equivalent is equal to delta V over R1 plus delta V over R2. And as you can probably already guess, my delta V's nicely cancel, and that's where we get our known equation that 1 over R equivalent is equal to 1 over R1 plus 1 over R2. Alright. Okay, so that's a quick overview of the resistors in series and parallel. So I'm going to do question number 1 from lecture worksheet 4. I'm going to write this down. And we already did this in lecture, but it's, again, just a recap. So I'm going to do lecture worksheet 4. I just write it Q1 for question 1. So the first question says, for the circuit provided in class, okay, hopefully I remember the circuit, find the equivalent resistance between point A and C, and what is the current in each resistor if a 42-volt battery is connected between point A and C. Alright, so maybe it's a good idea if you upload your worksheets before I do these. But let me draw the circuit first. So I have location A that goes through a first resistor, a second resistor, and then it splits in parallel. Resistor 3, horrible resistor. Resistor 4, down, and then location C somewhere over here. Okay, so here I'm going to have R1, R2, R3, and R4. And somewhere here we have location B, just so I can add resistor 1 and resistor 2 first. Okay, I'll use yellow now. Alright, so here I'm going to write that R1 was 8 ohms. R2 is 4 ohms. 3 is 6 ohms. And if I'm not mistaken, R4 was 3.0 ohms. Okay. Alright, so let's first combine these circuits as if I have two equivalent circuits. So I want to convert the circuit to have, I'll put, I don't know, step A. I want to have A, one equivalent resistor, and then here I have B, another equivalent resistor, and here I have C. So I'm going to call this first resistor R equivalent 1, R equivalent 2. Okay, so let's find R equivalent 1 and let's find R equivalent 2. Right, so for R equivalent 1, so here R equivalent 1 will be the combination of R1 and R2, which are resistors in series. So to add these R1, R2, I can just simply add these resistors. So this will be R1 plus R2, which is 8.0 ohms plus 4.0 ohms, and this gives you 12. Can I squeeze 12 here? Let's see. Yeah, not bad. Alright, so then I have R equivalent 2. So R equivalent 2 will be for resistor 3 and 4 combined in parallel. So for resistor 3 and 4 combined in parallel, I have 1 over R equivalent is equal to 1 over R3 plus 1 over R4. So I'll continue here. This is equal to 1 over 6 ohms plus 1 over 3 ohms. That's a 3. And this is equal to 1 over 2.0 ohms. Okay, so remember, lowest common denominator multiply. Okay, multiply this by 2, multiply by 2. Alright, so this gives me that R equivalent 2 is equal to 2.0 ohms. Okay. Alright, so now let's combine. Let me put another box here. Now let's combine R equivalent 1 to R equivalent 2, and I'm just going to call that R equivalent. So these two are two resistors in series. So if I have now, again, let me use yellow, location A, one resistor, going to be, call this R equivalent. Okay? So here I have R equivalent is equal to R equivalent 1 plus R equivalent 2. So my R equivalent 1 was 12.0 ohms, and then R equivalent 2 is 2.0 ohms. This is equal to 14 ohms. All right, so now we combined. Let's go up a little bit. This circuit with two resistors in series and then two in parallel into one resistor equivalent between locations A and B. Okay, so first is what is the equivalent resistance between point A, oh, this is a C, between point A and point C. Then the solution is 14 ohms. All right, now let's get B. Okay. So B is what is the current through each resistor if the voltage of 42 volt battery is connected between point A and point C. Okay, so here I'm going to have let delta V. I'll put here a B for battery is 42 volts. Okay, let's go back to white. All right, so we did this before, so let's work backwards. Now I have, remember that R1 and R2, these are in series, and that R3 and R4, these are in parallel. Okay, so what we're going to do is we're going to get first the equivalent, the current for the equivalent R, and then we're going to apply the junction rule, which we will then define as Kirchhoff's law to get the currents. All right, so I'm going to go a little slower here because we're going to do a bit of repetition with what we're going to do right now. So I'm going to have I, which is the current, is equal to the change of voltage over R equivalent. Okay, this is Ohm's law. V is equal to IR. So this is equal to the potential difference is 42 volts given by the problem, and the R equivalent we just found out to be 14 ohms. So I is 3.0 amps. Okay. So if I have here again A, one resistor, and B, you have a current, and this current will be 3 amps. The resistance is 14 ohms, and the potential difference between A and B is 42 volts. All right, so if we remember our properties for currents in series, then just the pen. For series, we have that current is same through R1 and R2. Okay. So this means that I1 is 3.0 amps and also I2 is 3.0 amps. Okay, so we got two solutions because of that property. I'll put a box here. Alright, so what about I3 and I4? So now let me draw the circuit for the part that we have in parallel, just the part that's in parallel. So imagine here we have B, okay, and then B can go up and go through resistor number 3, which remind you is 6.0 ohms. And I can go here to C, can go down, and this was R4. Handwriting's getting so ugly. 3.0 ohms. Okay, so imagine we just have the part that is in parallel. Alright, so I'm going to separate this current. Okay, so what I'm going to do is the following. We have I. This I is the current that we just solved here to be 3 amps. Okay, here we have a 3 amps. So we have I, which is 3 amps, and now this I here at this junction, which is what we're going to call junction rule, which I'm going to go do a formal lecture on that. here this junction, it gets divided. It can go up. I'm going to call this I3 because of resistor 3. Or it can go down. I'm going to call this I4 because of resistance number 4. Okay. What I did right there, although it looks common sense, is called the junction rule. And if I do this as an equation, my equation will be that I is equal to I1 plus I2. Okay. Now, when we have potential differences, voltages in parallel, what happens is that you have the same potential throughout the circuit. So here we have the change of potential. This will be the same because you have parallel. So the change of potential through the 6 ohms is equal to the change of potential through the 3 ohms. So now I'm going to combine Ohm's law with these two conditions, the blue condition and the red condition. So I'll remind you that here, Ohm's law, I'll write it here, Ohm's law, we have delta V is equal to IR. Okay, so here we have delta V will be the following. So the delta V for the 6 ohms is I3, because that is I3 that goes through resistor 3, times R, and R is 6.0 ohms. And that is equal to I4 3.0 ohm. Okay. All right. So I can divide, let's divide both by 2. And I have that 2I3 is equal to I4. Okay, this is a condition. So 2 times I3 is equal to I4. So I'm going to sub this equation, I'm going to call this equation B, into my initial equation. We call it equation A. So we have the following. So remember that the total was going between I3 plus I4. Okay. So the green, the total was 3.0 amps is equal to 2I3 plus I3, and this is all in terms of I3, and almost there, 3.0 amps is equal to 3I3, so I3 is equal to 1.0 amp. Okay. All right, so that means that if I3 is 1 amp and the total is 3 amp, then by default I4 is equal to 2.0 amp. Okay, so this is the first question from lecture worksheet number 4. Right, so I recommend you to review this, go over this video a couple times, pause it, try it by yourself, and then you can move on to the second one, which I'm going to introduce Kirchhoff's laws. If you have any questions, please let me know.